at the university level, they aren't as good as addressing that. Here it is.
So how is the homework going?
Slow.
Slow means because you guys didn't have any time to work on, or is it that the concept is just too much?
Solution are really long.
Solutions are really long. So it takes a long time in each one. Okay, okay. Yeah, okay. So if there was, so it is, you understand the point, it is just that it is too long.
I think from my perspective, there's some of the nuances, tricks and things from calculus that I haven't used in so long that I could make my life would be a lot easier. But so I have to kind of go back and
which is equivalent to saying that it is not completely, you're not comfortable with it.
well, it's not.
Yeah.
Once I see it, it's like, oh, that's right.
Yes.
But it's the.
What about
I
this?
think my brain is old. Starting to give out on.
Earlier, did you get a chance to catch up? Or you still, I mean, I'm not. So, yeah. Luke, how was the homework? Have you started?
Yeah, I started. It took me a while to
See what it is?
get to some of the concepts, but I think it was a bit, it was starting to go better. But not sure.
So if I have to help you with the homework a little, what do you guys suggest? What should I do? Abdullah, how was how is the homework going?
I'm trying.
Fine. Something more explicit might help, like, is it hard? You think you will get it, or?
Yeah, I'm trying to relate reading the lecture again and trying to solve it.
So if I just don't worry about the homework and keep going, that will help, or should I do some examples on the homework?
I think we should do more examples.
For example, okay. Michael, how is the homework?
Really slow.
Really slow. That's again not
Yeah.
helpful. So examples would help. That's the fine. And Aryan, you said you finished the homework.
It's almost.
Yeah, so you have a handle on it. It's just you're saying it's long. Long is okay. I feel. How long? How many hours did it take for the homework, including the understanding part?
Something takes me for example 2 hours just to.
Oh wow, 2 hours.
6-7 pages.
I don't expect it to take that long, but maybe you're being very careful. Maybe you're doing, because yesterday you pointed out that you were worried about some very subtle points, which is true. Maybe you're doing more than what I expect. So, but it's good that, okay, so you're able to proceed. So I think hopefully it will take 2 hours. Each problem is it. Okay. I would not like the teacher. That's okay, we'll see. Hopefully after this lecture. So I will do examples. Anyway, I'm supposed to do it in a particular context. Like I would have tried to do some specific popular example like practice structure on geodesics and so on, and formats theorem. These are standard minimization problems. But I'll first do just as if we are doing math, like when we do calculus, we just explicitly do examples without any context. Right? Give me a function and try to do the derivative. Right? And that is the idea as a user. You have to get used to that level of usage that we should be able to do the derivative just blindly. That's what we would like to reach, but at the same time, in the beginning, I'll do the long way also. But we need to get used to doing it in a short way also. Okay, so let's see, before I proceed, homework, right? So we have a homework 2 that was due today, that's been postponed. So this was due February 1, which is, no, February 1, right? Yeah. 3, Wednesday, no, Tuesday. It is Thursday, right? I'm going to go ahead and post homework 3 soon after the class, and we will have this still due February 8, which is a Tuesday. And this will be related to whatever we are doing. It's going to be very, it's just that it will be more contextual. There will be a story around it. Currently, we are just doing functional derivatives there. It will be specific.
Do every Thursday instead of Tuesday.
Oh, you want to make it Thursday?
Every Thursday.
Every Thursday, but it won't stay. How about this? Officially, I'll keep going. I think this came up another semester also. You can, officially it's due on Tuesday, but you're allowed to submit it by Thursday. That way what happens is that I can keep going. You see what I'm saying? I don't want to slow down based on it unless it's necessary. For example, if it happens that I spend all the time working on examples and I realize that you're really struggling, and then I will have to really slow down the whole course. But currently I feel that I can keep going with the course, just that I'll treat all the things I have to do as if they're examples. Okay, I thought I'll change.
It's because we are all really busy from Tuesday to Thursday.
Okay. How about that? Officially, let's do this. It's the first request. Let's make it officially due Thursday. But maybe not all the time, okay? Because it gets harder for me, if that makes sense. So that's 3, and this will be February 10, Thursday. When there is only one due date, then I have to teach around that. So course might get slowed down. So I'll try not to stick to Thursdays, but feel free for you guys to submit on Thursday. If that makes sense. Is that clear? So I'll keep going. Okay. And there's a picture also. If I can find it. That's all Thursdays. So then is this convenient? Thursday exam, so that suits, right? Again, if there is an inconvenience, you tell me in advance to make it last moment changes. Yeah, so we would like to understand functional derivatives. Let's do examples. So the easiest example we did as example 1, right? Let's say this is a functional. By that I mean that y is not a fixed function, y is not a given function, but inside everything else is given. So let's say this is A, that's B. It doesn't have to be A and B, it can be minus infinity plus infinity, and that's perfectly okay as far as it's a well-defined integral. Let's say this is just x, and this is derivative of y with respect to x. Oh, that is x prime. Notice this is if I knew y, so for example, if y was sine of x, right, then that's a number. Right side is a number, there is nothing this can depend on. Instead, we are saying, I don't know y. Like y is open as a function, it could be any function. And then we ask, what if we change the function a little bit? So y is a function of x. So let's see, y, so this could be an arbitrary function. If I change this function, by that I mean, so that's a new function. If I change that function from y to another function, y prime, how does my left-hand side change? So that's what it means by saying it's a functional. Like it's not dependent on a variable, instead it's dependent on the function itself. And of course, it is dependent on the integral, so accordingly this will change. So how do you, so we can define a derivative associated with this change. So let's say this is y of x, or y of x prime, it's sort of there, and this is y plus delta y. So I should really clarify this. So this is y of x prime, and I make a small change everywhere. So this small change is a function of x. So this is delta y of x prime. This delta y should be read out as a single piece. It is a function, right? Delta y is a function of x prime. It's a small variation. Delta y just says that it's a small variation, but it's a function of x prime. That's the important thing. This is an arbitrary function of x prime. And delta y just represents that it's a small change. At every point, there is a small change in this. Could be zero also. So that's in words. So how does my left-hand side change because of that? So I say this is y plus delta y, an arbitrary change, and that's equal to a to b x prime. This is here. Let me write this as y of x prime plus delta y of x prime. So I'm going the long way, and I'll come back and do the short way. So that's your variation. Pick out the first piece. So this is the same as a to b, x prime, b by dx of x prime, y of x prime, plus a b x prime, that's delta y of x prime. Again, stick to the fact that this is a label, right? Delta y is a single label. Try not to move the delta onto the left. Like this is not the same as delta of d by dx prime of y of x prime. That's another quantity. This is a variation in this derivative. That's the way you would read it. But here, this is a single piece. Delta y was just a label, like for the small variation. So you don't want to move that delta in there. So that's original I of y itself. So this whole thing is I of y. So that's your small change if you want. Due to the small change in the function, how did the functional change? So I y plus delta y. So y plus y minus of y is equal to a over b x prime derivative x prime y. That's your small change in I. Let me define this as a variation in I. We want y. That's a change in y. But then you say, I'm interested in a derivative. So derivative will be change in I as a ratio, right? Over the change in y itself. So let's see what is I, variation in the functional, due to a small change in y. That's the ratio, if you remember the derivative idea, but we don't write the limit if the y tends to 0. It's understood that this is a small variation. So that's equal to 1 over, if you want the way this is written, that's 1 over delta y x a b x prime x prime over now. Here is the point where so this is a lot of interpretation in here. You actually take this inside the integral. As far as a procedure goes, you're just saying that, oh, this is x prime integral. You're taking this delta y inside the integral. It doesn't change anything. But the interpretation is that you're making a small change in y with respect to y. So that's there are interpretations involved. But as far as procedure goes, we are just mathematically allowed to take a function of x prime inside an integral, and derivative goes through the derivative also. Any questions at this stage until here? Now, this we say is a delta function. We say this is the change in y at any arbitrary point x with respect to a change in x prime. So if you make a small change here, how does this change get affected by that? And you're saying these are independent variation, and that requires that this is a delta function. And once that is reached, you simply say this is a to b x prime, and derivative x prime delta of x minus x prime. Do integration by parts and use the fact that you have not changed, made any variations at the boundary, or actually, yeah, that's okay. Yes, I can do this at this stage, or I could have done an integration by parts at this stage also, like here. So that's also a common to do. Here I can directly use the idea of a derivative of a delta function. Derivative of delta function is you just act on the other side, right? So that's minus of derivative of the function that is in front, so that's x prime, which is equal to 1. So it's minus 1. Or this is x. Or you can say x prime, and this is evaluated as x prime. This was in detail showing that how the variation affects y. First you make a variation in y, and then you take a ratio with that. But after a little experience, you realize that it is a standard derivative that you're doing. I can directly start from here, for example, this, and say that I'm doing I of y. So that's over delta yx. In fact, it directly enters this integral as if you're doing normal derivative, x prime x d by dx, very similar to what we suggested here, and directly reach this step. That's also okay if you know what's going on. And that's a delta function again. It's equal to minus of 1, right, from this step on. Like after a little experience, you directly start writing. You realize that, oh, these are all details. It happens again and again, so you can directly do that. So let me, any questions at this stage, the way I have presented it here? Little trivial. or what is the discomfort you had if you guys, hopefully you guys tried? Can you relate the discomfort you had with what I'm presenting, or is it too simple an example? Maybe I'll do another example. And we should.
That might be a little too simple.
Too simple, okay. Yeah, okay. So let's do another example. So let's say I of y. So this particular form shows up in what we will do if you are trying to describe mirage as a physical principle formats, you know. So irrespective of what it is, let's say we are having a to b dx prime, and let's say again x prime, and this time let's have 1 plus dy by dx whole square and square root. Right, so let's say that's your function for x prime. This is a common thing you will see, this structure 1 plus derivative of y with respect to x prime is a common thing you will see. And this is the origin of this is if you want to talk about a distance, ds is dx square plus dy square in a plane. So this is equivalent to saying if you have a function, this is x, that's your y, and that's tiny element here. That's your ds, that's your dx, that's your dy, that's your dy, sorry, that's your dx, dy, ds, right? And in the infinitesimal language, that's what it is. And often we are interested in the arc length ds, but you would like to, suppose you're interested in the perimeter of a curve, and you want to add this ds along, but you would like to integrate over x. It's usually harder to go along ds. You want to write it in terms of dx. So what you would say is that ds is equal to square root of dx square plus dy square. And you can either, if you want to integrate with dx, you will take dx out. And that's 1 plus dy by dx square. Of course, this is also equal to dy times square root of 1 plus dx over dy square. Either way. But often we are interested in integrating with respect to x, so we encounter this. But that's not always necessary. Sometimes it is convenient to work with y as itself and integrating over y also. And we will see situations where one is better than the other. Especially when you're working on a sphere, you will notice that there's a significant simplicity if you do it one way over the other. Sometimes the other way is not even possible to do. So the integrations may not be easy to perform in that case. Anyway, so that's a context where this kind of structure shows up in a functional derivative. But for us, this is just an exercise, right? So that's a function. And now let's do this. Let's do the simple way first. Let's do the hard way, right? So, not what it's a test. Right? So, this is not a bad weather problem. You see that? You hear the sound, right? So I don't have to do this. Okay. So let's use the same procedure there. We do y plus delta y. So I make a small variation in y, and the only place where y shows up is this. So I make the same change there. That's a to b x prime 1 plus. So this is dy by d. Let me write this slowly. Let's d by dx prime. I have to take the derivative of y of x prime plus delta y of x prime. But this is a single piece. Right? like this. Separate this out. I would like, notice here, somehow I shows up separately, right? So you want to isolate your I beforehand so that you can subtract things out. So this is inside a square root. It seems like a little work. So let's do that. So it's a to b, x prime, 1 plus this is by dx prime. I'm suppressing the x prime dependence plus x prime of delta and then the square. Expand this out again. E x prime square, and you have plus. There are now 3 terms here. That is 2 times dy by dx prime. Remember again, y is a function of x prime. So that's dy by d of x prime. This is delta y as a function of x prime. And there is a delta y square, but that's order square. If you allow me to write it, that's order square. Like remember your derivatives when you're doing it, you don't want to keep second order terms because first derivative will always depend only on the leading term. So whatever this is a second order term in delta y. This is my original IY itself. I want to remove it and separate that out. So let's it does go long. So this is what probably you're saying, right? It does go long. Let's do this. Okay, so take this out. So this is A to B, x prime, 1 plus dy or dx prime squared. That's my I, right? So I want to keep this out. And if I put that outside, what's remaining is how is it? So this is hoping. I removed this out, so that's 1. So this whole piece became a 1 plus 2 times dy by dx prime this is again function of x prime divided by this 1 plus by x prime square. This will also get divided by that, so that's, but it's order square. So is that familiar? I mean, by this I mean O. So this is like curly O if you want. So that means order square. Whatever is the small quantity that is, at least there are 2 of them. That's what it means. Okay, with me? Any questions at this stage? You seem to be wanting to.
Yeah, just a little bit.
Yeah.
I guess it makes me nervous that the like delta y squared term like comes with a derivative.
Let's okay. You want to keep that.
No, I'm okay with getting rid of it, but
Okay. How about this? Whatever it comes with a derivative, that's correct. Eventually, you expand this out, and there will be derivative sitting on it. Always, you want to move it onto the left. So maybe that's what I wanted to do that here. I think I missed it. This is best done at this stage. I should do the integration by parts, and then do the division. So at this stage, I should have integrated by parts if that discomfort is there. this is okay, but here I have presumed that, oh, there is nothing wrong with this derivative. This taking in was not completely convenient, right? That wouldn't have been necessary if I had done that there. I missed that there. Sorry, after writing there, I got an lazy. Did you see what I'm trying to say there? Okay. So it's almost saying, trust me. So derivatives, you can do the derivatives first, and that's perfectly okay. Okay, so you can. So how about this quiz? Okay, so the quiz is do the same exercise from here to here, like start from this point and reach here. But I want you guys to do the derivative by parts at this stage. If you do the derivative by parts or integration by parts, sorry, you will hit here and there will be a total derivative term. So there are two terms right at this stage. And then do the division and you will get the same steps, but then the argument is a little more neater. So, is that clear what the question is? The quiz question is? Okay, so let me go through it. I mean, I think it's an important piece. So let me go over it instead of putting it on your head. Okay, so let me go over it. Okay, so instead of this process, let's take this here and say change in I as a function of y. I should be changing it, but that's not a good thing. So, oops, this is functional, and this doesn't write. This is delta I of y. That's this piece here. And let me first rewrite it. A to b, dx prime, e by dx prime of delta y. That's just rewriting that. Do the integration by parts right at this stage. This will give me a to b x prime by dx prime of x prime times delta y. X prime and e by dx prime of x prime, which is 1. This is 1 times delta y. Clear? Right? Which is happening here also, but it is happening at this stage, right? Where I integrate it by part. But this is now when I divide, this is much more neater because I'm not taking it through a derivative. So if there is any concern on that, you escape. Now you do the derivative. So maybe at this stage, I should also say this is x prime delta y of x prime. Evaluate it. So at this stage, I can say this is x prime equal to b and x prime equal to a. So yeah, let's do this. So this is a to b, the x prime delta y of x prime. Do one more step, right? In this stage itself, substitute this. So this is b times delta y of b minus of a times delta y a. Notice this is the variation in y, the variation of the function y at point a, right? That's what this means, the delta y. And this is a to b prime. Any questions at this stage? It should be all clear. And now you do the ratio. Change in I over change in y with respect to x. So that's equal. To go through it. So this is b change in y p over change in y at x minus a times change in y at point A over change in y at point x, and minus, here I take it through, that's a to b x prime. In this way, this comes out nice, slightly neatly also. You say that this is the change variation in y at the boundary b with respect to x. And if we say that that's zero, that need not be the case. We can change the points at the boundary also. So we are saying that the variation at this point is kept still, right? It doesn't have to be the case, like we have changed that also. But in the beginning, for first few weeks, we won't make that variation. Later on, we would like to make that variation. There is nice things out there also. But if that is zero, then this goes away. If that is not zero, that's need not be the case. That can also contribute. But if that is zero, if variation at boundaries is zero, that means only the numerator, right? We're not saying that it is independent of this. This is the fact that we're not making the variation at all at y, right? That's slightly different. And y(x), that's equal to b times 0 minus a times 0. So that's 0, right? And minus of this we interpret as our delta function, and which is minus 1. From this point on, it's straight forward. So, so the point is that even if there are derivatives, you can take away move the derivatives to the other side all the time. Even if it is second derivative, third derivative, do as many derivatives you need on to the other side. And if this is a secondary, I think your point was that this is a square here. Even then, you can take the derivatives off, and then you say that, oh, this is a second order case. I don't want to keep it. I'm going to avoid keeping that here because it's very quickly gets very messy, and I don't mind really the messiness. It's just you don't have space. At some stage, you should keep the second order at least once in life. Do that convincing. Now, this really doesn't contribute. So I believe in that thing that you should at least once do that. But here, that's not. It's not very instructive. Okay, is that clear? Any comments? Aryan? Okay. Abdullah? No. Okay, so let's go back to this. That is it. Let's go. Okay. This still doesn't help because this is second order, but and I can neglect it. But this is inside a square root, right? So I want to take this one out so that I can move this to the left hand side. So if I want this to be released from the square root, I have to expand this. And remember, in calculus, we always expand. Always there is a series expansion involved, and that gets very in calculus. It's tricky because first we introduce the idea of a derivative. So Taylor expansion is often depends on the derivative itself. So, but I think best way to look at it is that series expansion is independent of Taylor expansion. Like each function has a series on its own. It's just interesting that a series can be interpreted as a derivative expansion, and that's what Taylor series is about. But series expansion is independent of like sin x has an expansion independent of the concept of calculus. But it can be interpreted as a derivative. I think so. Criticize me. That is, I'm thinking right at this point, it seems to be the case. But criticize. Okay. Okay. So I want to series expansion. So our idea is simple. This is one. Whatever this is, there is this small tiny element here. It's small, so I can expand this, again, that could be a concern that, oh, something small doesn't mean that derivative of that something small is also 0. But if whatever the derivative is, we will take care of it. When you take the differentiation by parts, we will take care of that. And if that is an issue, it will show. So expand this out. What is the series expansion of 1 plus small x square root? So that's 1 plus 1 by 2x. So the 1 by 2 comes from the binomial power of 1 plus x, like that. And there are higher orders there, but I'm not interested in the higher orders. So do that here. So this is A, B, x prime 1 plus y dx prime squared 1 plus 1 by 2 of this, 2 goes away, and I can say dy by dx. Often, because you have to write so much, people come up with notations that y prime means derivative with x prime. I'll try to avoid that, just at least on the whiteboard, but you're allowed to do that. So often this gets really compressed whenever you write that notation. Y prime often is used as dy by dx prime. And in physics, often you have a time derivative, which is more special, and you say y dot is actually y by dt, if there is a time also in the picture. So that's a notation. I try to avoid it, but feel free to do that as far as it's unambiguous. It's clear what you guys are doing to me. That's okay. And this is 1 plus. And that's higher orders. By that I mean higher terms. And that's that clear? The one here is nothing but my original I. So I can move it to the left and I get delta I. So this minus this first term, but this has to multiply that also. Right? So that's equal to A, B, x prime, x prime. Notice these two terms are identical, except this is a power of half, that's a power of 1. So when I multiply this in the denominator, I'll get a power of half. So I get derivative dy by dx prime, d by dx prime, delta of y divided by 1 plus. So that's change in I. Let's do the same idea. Let's do the integration by parts at this stage itself. So that's a long way. And then I'll come back here and do the short way. Also. Any questions until now? Okay, so do the integration by parts. Notice I want to rewrite this in this form, right? That helps. So this is d by dx prime of delta y of x prime. Whatever this is, this whole piece is some known or some function of x prime, and there is a derivative acting on the change in y. So this is the variation in y. I want to isolate. So I want to move that onto this. So you do change in I equal to A to B x prime total derivative x prime y x prime over times delta y. And minus of e prime and get the derivative only there. Now let me write the delta x prime first, then I don't have to write the parentheses. Delta y x prime and set the derivative on the rest. Okay, I agree that it goes long. We'll make it a little short. Okay, I'll find it. I'll tell you short also. Okay, notice again that when I evaluate at A and B, this becomes, this whole thing evaluates at B and then evaluates at E. There are 2 points there, right? So change in I, the function of y is equal to x prime is replaced with B now, right? So it's B times dy. Let's use that notation. So this is dy by dx prime is going to be y prime. So this is y prime of b over 1 plus y prime squared. And this is y b over 1 minus of a times y prime of b over 1 plus y prime squared. And this stays, right? This whole integral stays. Prime y prime, yeah, y prime, y prime plus y prime squared. Divide it out, delta I y over delta y x. This is at the variation. If there is no variation on the boundary, this will go to 0. Y prime b 1 plus y prime b squared. And this is delta y of b delta y times, which is 0, minus I prime of a. Right. And delta and here there is a, when I do this, there is a derivative here that comes out as a delta function, and that's a e x prime delta of x minus x prime of derivative x prime fine. I'll let you write this explicitly now. Go back. Okay. This was 0, that's 0. This is a delta function integral. The delta function integrals are easy to work on. That's x prime. Easy to work on, just replace this whole thing with x. Wherever there is an x prime, I replace it with x. So this is equal to d by dx.
You move the camera.
Oh. doing the small angle system, but then we can times y by dx. Now all x primes have changed. So that's and that's it. It's possible to, and now you might find it convenient to operate this, or you say, oh, this is a total derivative, why should I leave it here? Operate this. But my recommendation is that leave it as it is. Why? Because what we will need is that we will often set this to 0. When you set this to 0, derivative of this will make this a constant, whatever it is in there. So that is because we know what we are going to be doing in the later stage. At least I know what we'll be using this for. So it's not necessary to operate it, but if you feel compelled to operate it, why should I leave this in this form? That's also perfectly fine. That's understandable. This was a long way, as I said. I actually separated this. First, I evaluated the change in I, and we isolated this term. But there is a slight simpler.
Is that minus?
Huh? Is that a minus? No. Oh, there is a minus sign. Yes, because this minus sign, right? Yeah. Thank you very much. Yeah. Okay. Anything else? Any questions? So, but I'll do this again in slightly short way, pretending that we are doing derivative and slightly short. Okay. So let's erase this. So once you build a lot of trust in whatever we are doing is not nonsense, then you can actually take liberties, right? So then what you would do is, again, now we're going to take the derivative with respect to y, right? So now at this stage, really pretend that y is a normal classical derivative, right? Think of this y as a derivative until the last stage. So what will you do if it were a normal derivative? You will do, so this is delta y of x. So normal derivative is take the 1/2, right? So do all that. The x prime, it doesn't touch, there is no y here, so I don't have to touch that at all. This is 1/2, right? So it's 1/2. And this goes in the denominator, 1 plus dy by dx prime square. So I'm just doing normal derivative here. And then eventually I have to hit the derivative itself. Like eventually I have to hit the derivative of y. But before that, there is 2 times dy by dx prime. And now is the time where I hit my derivative. So there I say, so this is, all this was normal calculus. At this stage, I say this is dy dx prime. When I reach that y, I have to pretend that I'm doing the functional derivative. And that's delta y over x prime over x. Until I reached here, right, again, I was doing standard derivative. Is that clear what I did? I pretended as if I was doing a y derivative with respect to y. Did until here, until I was actually reached the argument. There I said, oh, no, this is not my usual calculus. I will do this a derivative, functional derivative. And then I switched my language and I said functional derivative. And that is, but that gets away from the conceptual part where there are all these detailed, subtle things here. And all these are important. It's not necessary that all this is true. If you get convinced that all this is true and it will surely work, then you can do this. Right? If you, if I question you here, then you should be able to answer somewhere in the detail. But this is mechanically, this works. And now what is happening is that this is nothing but a delta function, right? So what has happened is, this is just one step, right? So I'm almost there at the answer. That's a to b, x prime, and dy by dx prime over 1 plus dy by dx prime square. And this is derivative of a delta function. You know what a derivative of a delta function is? Operate this derivative on whatever is not having the delta function with a negative sign. That's negative of e by dx prime of x prime by, oh, now it's x, right? Because I switch, I evaluate this at x. Well, that's it. Right. So almost 2 steps, right? This was more for elaboration. So almost 2 steps. You can do it. Now, when are you allowed to do this as far as assessment goes? Unless I ask you, if I ask you, like for example, this exercise, this particular homework, I'm asking you to show that, evaluate the functional derivative. Make sure that if I ask you that in the exam, then you have to show the details, right? Show the details, steps. But anytime else, if we are doing a functional derivative, you can directly use this. I'm okay with it. We only need to do the derivative. I don't mind. I don't want the details in there. But you should know how to do it, because in the exam, if I or somewhere else, if I ask you evaluate the functional derivative, then you should know the details. In your homework, I would say I'll recommend that at least 2-3 problems work out the details. And once you get in the first 2-3 problems, evaluate the details, like Irene said, it was taking 2 pages, or he said 7 pages, right? So I think if you write all the details, and like maybe if you're doing it for the first time, you will write more steps, right? So it's I think I can relate with what Irene is saying. But after a while, so after 2-3 problems, when it is the same repetition that is happening, then you can directly stop. Is that reasonable? Okay, so Aryan probably finished it, so you can finish multiple less time zero, but I'm sure it will help. Somebody won't be waste. Reasonable? Is that clear? Questions now. So that must be like functional derivative is not generally it has a lot of conceptual problems, even at this stage. Whenever you're in an unknown territory, it is not easily taken with it without a grain of salt. It's pretty much like delta function. Even now, people have a lot of hesitation with delta function, but once you use it a lot, then you know that yeah, this works. In this context, it works great. Like for example, electrodynamics can almost not do it. Not function in certain contexts. Even quantum mechanics, right? The delta function completeness relation is delta function. So plays an important role. So. Okay, questions.
So just something about like the exam. If you want the details, would you mind like in the exam question saying like evaluate the functional derivative like and show all the details? Just
Sure. That makes sense. Yeah. Oh, how about that? Yeah, maybe this. Unless I ask you to, you don't have to show. Reasonable.
Yeah.
If the question doesn't say it, then you have the liberty to not show. So if I was not careful enough to write it in the question, then you don't have to be careful enough to. Don't assume that's it. So by default, you do the short way, and that's perfectly fine. That is my point. And later on, anytime you have any concerns, you can come back and look at your notes, and you know that it exists. That is a formalism for that. But we will be users and we will just do this directly. That's all we need to do. That's what I would like you to do. Because you cannot spend at every step doing the derivative. This is called ab initio method. I think that's what in calculus you do it. At least when I studied calculus, we used to have to show the derivative using ab initio method, and you have to do it this whole process. Not for functional, there is the usual limiting process, right? For derivatives of sine function, for example, use it. Okay, so yeah, so that's reasonable, but I will ask you guys to check it whenever it's needed. Okay, I have 10 minutes. So let's yeah, there's a nice little example in your homework problem, right? Where you have to show that the shortest distance on yeah, in your homework, you say that, so this is geodesics, right? Is it readable? Geodesics. Readable, Michael? So let's say you are on a plane and you
Turn the camera.
oh
It might not be readable. Oh, it's fine.
not readable, right? Is better? Oh, sorry, I cannot read it. Okay. You guys are young. Okay, better. Oh, it's double. Hopefully, so let me know. Okay, so there's 2 points in a plane. Let's say x1, y1, and x2, y2. And what's the shortest distance between the two? Let's say it's plane in the sense of no speed changing. Like, what's the shortest distance between these 2 points? You will connect it by a straight line, right? That's and you prove this in your homework, right? That's your exercise. You prove that that's actually straight, and you will actually show that you have to just show that you have to find the equation of the straight line, and that's I can do that very quickly. How you will do so? Let's say you don't know that this is a straight line. So let's say this is some arbitrary path. I'll only give the gist of what you're supposed to do. And so this is a help with your homework. But I want to construct a similar problem on the surface of a sphere. Right? So that's x1 to y1. So what's the total length, the perimeter of this? So let's call this the perimeter, right? P. Length of this curve, right? L. I think length of this curve depends on y as a function of x, where this is my x and that's my y. So that's the function y of x. So as a function for given a function y, my length of this curve will be evaluate this length ds, right? So that's my ds. Sum of tiny elements in the limit ds goes to small, and you keep adding them. That's your ds. But on a plane, ds squared is dx squared plus dy squared, and this is the same as dx 1 plus dy by dx squared. Is that readable? Yeah. Yes. Could be better, but right. And that's what it is. And now, how do you find the question is, out of all possible paths connecting these 2 points, give me the point for which this is the shortest. And when it is the shortest, the derivative will be 0, right? Whenever a minima problem comes in, the derivative of that function is 0. So you say that derivative of, so that for shortest, the geodesic is defined as change in L as a function of y divided by y. So this functional derivative is equal to 0. Right? So this is the definition of geodesic. Of geodesic. So you say, now I need to do the functional derivative. You get this functional derivative, and it'll come out something similar, except that this x will not be there, right? You can see that there's an x prime there multiplied by that. That if that x prime is not there, I don't do this. So it'll be this equation, except this x will not be there. Right? If that's not there, I get this equal to 0, right? This whole derivative is equal to 0. That means this is a constant. So you get immediately, you will see that, oh, this is dy by dx over square root of 1 plus dy by dx square is equal to a constant. And then your goal is to find the, oh, so that's your differential equation for the curve that connects these two. Show that that's a straight line. The solution to this equation is a straight line. That's a claim. It should come out to be a straight line. That's your goal. So from there, I'll let you guys do that. Okay, so that's a homework problem. But let's now at least construct the problem for slightly. If any questions on that? So that's your one of your homework. So now let's say same idea here. Now you're on the surface of a sphere. And let's say you're traveling from, you're flying from New York to Moscow. Or tension is just go from New York to Moscow, and then you would say that you want to save fuel, don't want to go around a long process, and you would like to go by the shortest path. And you will often notice that when you're going from Europe to crossing the Atlantic, you almost go by Greenland, right? So you go all the way there and then come back here. Where do we go all the way to Greenland? Why not go a straight line? If you draw a map, a short straight line would be this, right? If you take a map, if you draw a straight line, you will not touch Greenland. It will be pretty much, you will touch Spain or something. Instead, even if you're coming from Netherlands, which is close to Spain, you go all the way top and then come back. Why do we do that? Is there a reason? Is it because you want land, you like land, you don't want to fall on water? Yeah.
Because of the surface of the sphere, when you go straight across, you're going a greater distance.
Correct, exactly. So just because you've opened the map into a flat sheet, that doesn't mean that short straight lines there will translate itself as shortest path. On the surface of a sphere, this is the shortest path. And how do we decipher what the shortest path is? Here is a procedure. So what you do is, given 2 points, you want to find a circle that goes through the 2 points and has a center as the center of the sphere. Okay. Think of a circle that goes through the 2 points and has the center as the center of the sphere. That's called a great circle. So a great circle is, so let's say again the same problem. So this is the center. And now, if I have 2 points here, I want to think of a circle that passes through these 2 points, and it has this as the center. There's a unique circle of that kind. And we go almost touching Greenland because a great circle touching points in Europe and America usually passes through. I mean, you have to go a little north to get that. Right? And that's the idea why we do. But then we should know this should come out clearly as a solution, right? Great circles should be this minimal path. In fact, you say that on the surface of a sphere, a straight line are great circles. Right? A geodesic, by definition, is a straight line, but then you say, oh, it's not at all straight, but it's our concept of a straight line. Geodesic, the shortest distance between 2 points is a straight line in a curved geometry. And light happens to take that path all the time. Think of light in space-time, then it always takes the path. But more simplistically, the shortest path between 2 points is what is defined as a straight line. So a circle is a straight line, quote unquote straight line on the surface of a sphere. Okay, so how do we proceed to get that? So if you want that equation, let's in the last 3 minutes, let's do the same thing there, right? On the surface of a sphere, I have ds. I have a sphere in spherical coordinates. If you're on the surface of a sphere, radius is fixed. So the only variables are angle theta and phi. In space, I have radius, angle theta, and angle phi. Right. But radius is fixed, so I don't care about that. I'm on the surface of a sphere. It's the angle theta and angle phi that is important. So what is my length ds on the surface of a sphere? In general, it is dx square plus dy square plus dz square. On the surface of a sphere, it is r square, which is constant, r square times d theta square, plus r sine theta, r square sine square theta d phi square. That's my line element on the surface of a sphere. How do I get that? Go into spherical coordinates. So this is my change in theta. Make a small element here. If I can motivate that. This is angle d theta. And that's my d phi. That's my z. That's my x. And that's my y will be in this direction. If this is d theta, if I am having this rectangle, this is an arc length. So this is r d theta. And this will be, this length here will be r sine theta d phi. How about this? That's a quiz I can give. Show that or motivate this, right? Geometrically motivate this. Motivate the line element on the surface of a sphere. Motivate that and show that this is actually true. Basically, this geometry, that's what I'm looking. So if you look up why the line element on the sphere is so much, you will see this diagram shown and try to motivate that diagram. That's all. And we'll come back and do the geodesic on the surface of a sphere next time. And I'll stop here. Thank you.